Hello and welcome to the webcast titled VITA 93 QMC, enabling modular, rugged, high-performance computing applications. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. To learn more about military embedded systems, please go to militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speakers today are Matt Burns, Global Director, Technical Marketing with Samtec, Jake Bregelman, Vice President of Business Development with New Wave Design, and Robert Greenfield, Director of Marketing and Business Development with Acromag. This event is sponsored by Samtec, New Wave Design, and Acromag, and hosted by Military Embedded Systems Online and Open Systems Media. Now, before we begin, I got some housekeeping items to go over with you. This and all Open Systems Media webcasts are copyrighted. It may not be recorded or used in any way without the express written consent of Open Systems Media. The webcast will consume about 40 to 45 minutes, leaving the remaining time for the question and answer session. Now, let's take a tour of your viewing console. You'll find on the right-hand side an area where you can enter your questions in real time. We encourage you to ask these questions throughout the event while they're still fresh in your mind. Then we'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question. Otherwise, I'll hand it out equally to all the speakers. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the webcast. Please note, as much as we'd like to, we may not get to all your questions today. In that case, someone may get back to you after the event with more information. Now, across the way on the left-hand side, there's a resources section. That's where you can find today's slides, speaker information, and biographies, etc. Two additional features that we're really excited about. Your console is now customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. Expand them to get a closer look, or close them to have the presentation window automatically resize around them. For maximum screen size, close them all, and or use the full screen mode in the upper right-hand corner of the presentation window. To bring them back, just simply click on the buttons in the bottom middle dock. In an effort to make our webcast more accessible, we've added closed captioning capabilities in nearly a dozen languages. To enable this functionality, simply click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This webcast will be archived online at the same URL you used to join today's live session and be available within 48 hours. Once up, it'll be available for at least 1 year. Now I'm going to turn over to Robert. Get us started, sir.
Okay, thank you, John. Well, hello, everyone, and welcome to this webinar on QMC modules, the new VITA 93 small form factor mezzanine standard. So here on this slide, we can see several QMC modules and a carrier card that is a PCIe expansion board. So the QMCs just plug into the carrier card, which you can see with the red arrows. So what is a QMC module? Well, the standard defines a mezzanine module that is small, yet scalable for great flexibility. The design is relatively economical for use in laboratory or industrial environments that typically prefer a front panel I/O signal access and can use available airflow for cooling. However, it is also very rugged for use in critical military systems that require rear backplane I/O in fanless conduction cooling schemes. And it employs high-performance connectors for reliable, high-speed I/O signaling and PCIe host communication. The module is 26 by 78.25 millimeters, shown here in the upper right with a US quarter for scale. And it has two connectors, one for I/O and one for PCIe. Below, the module is shown with the Skyline heatsink installed for conduction cooling. Oops, jumped too many slides there. Okay, so the initial incentive for development of QMCs was the need for an I/O mezzanine to support the new VITA 90 VNX Plus computing platform, shown here as slightly larger than a credit card. VNX Plus was developed for defense and aerospace applications that don't have the physical space for a 3U VPX system, like those using a narrow payload tube with a diameter under 10 inches. Other applications with severe space and weight restrictions include small drones, ground vehicles, CubeSats, and smart munitions. However, you could see that the XMC mezzanine modules, which are commonly used on a VPX platform to handle a variety of I/O signal processing requirements, are much larger than the VNX Plus platform. Thus, we need a smaller I/O module capable of performing functions to support command control, communication, electronic warfare, surveillance, reconnaissance, and signal intelligence applications. The solution shown here is a VNX Plus carrier card that could host 2 QMC modules. So based on the use cases for VNX Plus, we set a number of goals. We settled on a size that would allow 2 I/O modules to fit on a VNX carrier card. We also tightly defined both the I/O and PCIe interfaces to simplify system integration. So to ensure the platform would be useful long into the future, we selected a connector capable of supporting at least Gen 5 PCIe speeds. For deployment in hostile environments, we were mindful of shock and vibration with screw-down security. Plus, we defined a conduction cooling scheme for fanless systems. At the same time, we wanted to remain compatible with many other popular modular computing platforms like VPX and PCIe boards to serve a larger market that would entice and support a large, diverse ecosystem of suppliers and products. So, despite the broad set of objectives, the primary role was to develop a modular open system architecture, commonly referred to as MOSA, to provide I/O expansion capabilities. As a result, QMC I/O modules offer a versatile solution to add various I/O interfaces on carrier cards and single board computers. They can also provide FPGA and GPU-based signal processing functions, or simply add high-performance data storage. Essentially, they are just a smaller version of XMC modules. Compared here at scale, you can see that in the same footprint that an XMC consumes on a VPX board, shown by the red outline, you could mount multiple QMCs and have plenty of room left over. So, another advantage of the QMC platform is the ability to scale up with multi-width modules when needed. This allows vendors to use larger chips like FPGAs and GPUs, as well as multiply the number or type of I/O signals and increase the number of PCIe lanes. Even a quad-width module with 16 PCIe lanes and 160 I/O lines is still significantly smaller than an XMC module, shown by that red outline on the bottom. So now people might ask, why not just use Mini-PCIe or M.2 modules, which are about the same size? However, these modules don't have a standard connector for the I/O interface. In contrast, all QMC modules have a simple board-to-board connection routing I/O through the carrier to connectors on the front faceplate or through the backplane. Without the same I/O connector on every module, you would be forced to deal with loose internal wiring or develop custom wiring harnesses and cutouts on the faceplates. So similarly, they don't have any standard method for conduction cooling. This makes system integration extremely complicated on rugged platforms, especially those using circular mil-spec 38999 connectors. So now Samtec will discuss the virtues of the QMC connectors in greater detail, but you could see that the host connector provides 80 pins for the host interface. This provides plenty of pins for 3.3 and 12 volt power supplies, 4 lanes of PCIe, a JTAG port, and an I2C system management interface. We'll discuss the management interface in a bit. And you also have a lot of ground pins to ensure signal integrity. So the I/O connector also provides 80 pins. This can support 40 single-ended I/O or 20 differential pairs plus the ground pins. The 80 I/O pins are organized as 5 I/O pipes. Each I/O pipe has 8 single I/O or 4 differential pairs and the individual grounds. This helps support isolated I/O interfaces. And you can multiply the I/O with multi-width versions and more connectors. An advantage over the Mini-PCIe and M.2 modules is support for an intelligent platform management interface, or IPMI. Now, system management interfaces are often used in a VPX or TCA chassis. But for QMC, an IPMC controller on the carrier card would communicate with the QMC modules over the I2C interface. Double EEPROM would hold the sensor info and module data, allowing the system to monitor the status, temperatures, voltages, and more of the QMC modules. So a new development is the VITA 93.1 QTM or QMC transition module standard. So this is a supporting standard that's nearly complete and defines a method to bring various cable connections to the front, like an XMC or PMC module could do, or to the back panel. The I/O from the QTM's connector is routed to the QMC module's I/O connector. So in this way, you can use the best connector for each module on a carrier faceplate or on a rear transition module. The bezel secures the connector to the faceplate and seals emissions. For example, you could use an RJ45 or an SFP port if you were using an Ethernet communication module. Variable stack height on these modules allows the use of many other connectors like USB, Oculink, RF, optical, and video interfaces. So here you can see how you could mix various connectors on a single carrier faceplate. For example, a PCIe carrier hosting 3 QMC modules could have a different connector for each QMC. So you could do optical, D-sub, RJ45, whatever. You could even have multi-width QTM modules for wider connectors like 68-pin VHDCI connectors. So as you can see, QMCs can support a very broad range of I/O interfaces. You got analog I/O like A to D, digital I/O like LVDS, or serial communication like RS-485. They can interface Ethernet, avionics, or industrial protocols like CAN bus. You can implement FPGA and GPU computation or video interfaces. And all these I/O options support functions like monitoring and control, test, simulation, conversion, imaging, sensor fusion, AI, edge computing, and much more. The small size makes QMC ideal, especially for smaller unmanned vehicles or high density computing in traditional defense systems. Whether the deployment is air, land, sea, space, or a lab, QMC has you covered. So in summary, QMCs are small but scalable. They're rugged with very high-speed interfaces. They have a standardized mechanical I/O and heatsink interface for easier system integration. And all this makes them extremely versatile, as you'll find out later. If you want more information, it's available on the Acromag website, or you can also go to the VITA website. So at this point, I'll turn over the presentation to Matt, and he can tell you more about the connector.
Thanks, Robert. Appreciate that introduction, and thank you for the overview of VITA 90 and VITA 93, excuse me. So, a lot of the introductions that Robert makes, we're probably going to just touch on for a minute or two, maybe from a slightly different perspective, but the same theme of a modular, rugged, high-performance computing platform is really the foundation and one of the key takeaways that all of our listeners, we hope you take away from our presentation today. So, Robert talked a little bit about, VITA 90, but, as Samtec has been involved with VITA 90 since its inception, even some of its predecessors with VITA 94. So, as that work has been going on for the last, let's say, 10 plus years, the necessity for a small form factor, next generation compute solution that was modular just made itself apparent, right? The VPX ecosystem has been around for a long time. It will continue to be around for a long time. But there are practical size limitations to what that platform can support. So, as VNX, VITA 70 for VITA 90, VNX Plus has continued to work its way through standards, the need for a smaller modular mezzanine also presented itself, and that effort around VITA 93 QMC really came out of a lot of the work that was going on with VITA 74, VITA 90, and the like. So something that was swap C focused, modular, small, dense, but also another area was VPX interconnect technology was designed and conceptualized back in the late 90s, early 2000s. So while there's been continuous SI enhancements to the to VPX platforms, there's still a practical limitation in terms of how fast the mezzanines are, or how fast some of the other interconnect solutions are there as well. So smaller, faster, denser is really, again, the genesis for why we're talking about QMC and how it came out of the VNX Plus ecosystem. This is just another angle to help us see why there was a need for VNX Plus and by extension QMC. So when you look at some of the standard VPX cards, you've got 9U size D, you've got 6U size C, you've got 6U size B, you've got 3U size A that are shown here. A lot of variability. These again are workhorses when it comes to rugged computing applications. They're not going anywhere anytime soon, obviously, but there's just next generation applications where a smaller form factor modular ecosystem is necessary, and that's really where VNX Plus comes. You can see that a typical VNX Plus card is about 70% the size of a 3U VPX card. It's about the size of a credit card, and without going all the details about VNX, you can support analog, digital, RF, optics, compute power, et cetera, at the ecosystem level. But there's also the need for I/O out the front of the solution. So that's where QMC has come. We found this slide working with one of our partners from Collins Aerospace, and they were kind enough to allow us to borrow it for several of our presentations. But to me, while I have an engineering background, I like to see things visually to help understand things a little bit better. And I think that this graphic showing, you having a 10-inch diameter ecosystem that needs a VPX module, you can see several of the projects that have supported that through mil-aero applications. But if you look at some of the newer defensive platforms that are being used by the U.S. and DoD, you can see that the diameter of these systems are getting smaller. So something needs to fit into a 7-inch tube, a 6-inch tube, a 5-inch tube, or smaller, and that's really where VNX comes into. It's smaller volume, it's swap C optimized, and because you're doing that at the system level, it also needs to be done on the mezzanine level as well. So maybe that's a little bit different perspective than what Robert showed, but I think it reinforces the general theme of how VITA 74, VITA 90 are necessary, and by extension, a smaller, faster, denser mezzanine like QMC. So when we look at QMC and look at it from a connector standpoint, what are some of the key differentiators that QMC offers versus XMC versus FMC versus PMC, some of the other interconnect solutions that are out there? Well, when you look at the existing mezzanine solutions, a lot of them use Samtec C-Ray interconnects. Samtec C-Ray is a wonderfully versatile, high-performance, rugged interconnect that's used in a lot of rugged computing applications. It's 1.27 millimeter pitch. It's vertical. It's right angle. Various stack heights. It's open pin field array. You can just support any type of signal type through the connector, differential pair, single-ended, analog differential pair, analog single-ended, RF power. So there's a lot of value add there. But at the same time, because the contact design is, call it 20 years old, there's only so much performance that interconnect solution offers. So, when QMC started being developed, the QMC working group looked for a next-gen interconnect that would support higher speeds, but also have a much smaller envelope from an interconnect standpoint versus legacy FMC, XMC connectors as well. In addition, Robert kind of mentioned this, there was a need for increased speed. C-Ray can't support PCI 5, PCI 6 in most applications. So, the interconnect family of choice that the QMC working group settled on was Samtec's Accelerate HD ultra-dense slim array connectors. This checks the box and a lot of the concerns. You're moving from a 1.27 millimeter pitch down to a 0.635 millimeter pitch. It's it offers multiple rows and multiple columns. In this case, 4 rows of contacts. There's various stack heights, as is shown here. The made stack heights for VITA QMC 93, we support 9, 11, 14, 16 millimeters. Those are going to be expanded with the new V93, the VITA 93.1 IO transition module that's in development that Robert talked about. The fact that you can have, again, flexibility, the various types of IOs you saw with some of the IO breakouts that are defined within VITA 93. That single pin can be ground, can be power, can be GPIO, high-speed differential pair. So the density, the small size, the flexibility in terms of stack height options, these are really the value add that the Accelerate HD product family from Samtec offers for QMC. Just a little bit more detail about the family. Samtec has had the Accelerate HD product family on the market probably for about the last 6 to 8 years. Again, we've talked about some of these key features, but just to kind of go through them to make sure the audience members are taking these away. Incredibly dense with up to 400 IOs. Commercially available right now, we support up to 4x100, 400 pin designs. Open pin field arrays, again, highly flexible, highly versatile in terms of pinout selections. Again, any one pin can be high-speed differential, high-speed single-ended, analog single-ended differential power. The extremely slim, the extreme close pitch of the interconnect we mentioned, 0.635 millimeters. We can support anywhere from 40 to 400 pin. Robert talked about how the QMC connectors are 80 pins, so 4x20. Stack heights as low as 5 millimeters all the way up to 16 millimeters. Here's something that's crucial. PCI 6, CXL 3.2 capable. So the Accelerate HD can support 32 gigabit PCI 5 data rates. It can also support 64 gigabit per second PAM4 data rates for PCI 6. So there's a nice performance migration path within QMC that gets you past the bottleneck that you'd have with FMC or XMC or some of the other ecosystems that are popular within mezzanine, within rugged computing. Something else that we also see with Accelerate HD is solder column termination versus traditional solder ball termination. This offers improved signal integrity and ease of processing. We'll talk about that more here in just a little bit. And then, for not that we expect there to be a huge power envelope for QMC, but any single pin on the Samtec Accelerate HD connector, the QMC connector, can handle up to 1.34 amp per pin. Obviously, that gets derated per pin based on how many power rails you have or how many pins you have, bringing current through. But again, very versatile interconnect. Very small, very dense, very fast, and it's ideally suited for small form factors like VITA 93 QMC. So, how do we know that the interconnect can handle the high-speed data rates? There's a couple of ways of looking at that, and we don't have time to go into all the signal integrity capabilities of the interconnect or looking at the signal integrity channels. Going from a VNX plus carrier to a QMC module or mezzanine. But the two data points that we're going to show here, both the insertion loss of the connector and the return loss of the connector help us to see or give confidence of the performance. So, if you think about PCI 5, that's a 32 gigabit per second data rate. The Nyquist frequency or the carrier frequency of those signals in the frequency domain, 16 gigahertz. So if you look at the insertion loss here around 16 gigahertz, you're right around 5 or 6 dB, across the breakout region, the mater connector set, and the breakout region of the connector. PCI 5, pad to pad, transmit to receive, something along the lines of 30. I think it's 32 or 36 dB across the PCI 5 channel. So you're going to lose 5 or 6 dB here across the connector. That still leaves you roughly 30 dB across the entire signal channel within a VNX plus ecosystem. Something else we also say, another signal integrity rule of thumb is anytime on a mated connector set, the return loss is greater than 10 dB, you've got really good performance. So again, right around 16 gigahertz, we've got a return loss of say, 12 to 13 dB. That 16 gigahertz Nyquist, both for PCI 5 and PCI 6, given that's PM4, just these two graphs, looking at that alone, we've got a good, strong level of confidence that the interconnect will support PCI of PCI 6. Samtec obviously has tested these interconnect solutions within the QMC form factor and various other form factors to prove that those performance levels not only are achievable, but are consistent and reliable across environmental variables as well that you'll see within a rugged computing application. We talked earlier, or just briefly talked about solder column termination. Maybe this is a new term or new technology for you if you're used to processing interconnect. A lot of interconnect solutions that Samtec offers and the industry offers, especially in BGA style applications, uses traditional solder ball termination, and that has its use in a number of applications or product families. But as interconnects get smaller, having there's a potential challenge with having too much solder attached to the PCB. Excuse me, not the PCB, but to the interconnect itself. So instead of using solder ball termination, Samtec has worked to develop what we call solder column termination. So some of the key, you can see the difference there in the illustration. Here's traditional solder ball termination. Here's solder column termination on the bottom of the PCB. Here you see a solder ball connector attached to a PCB. I think this is actually a C-ray. And then this is solder column termination using one of our newer Accelerate HD product families. So, by eliminating or minimizing the amount of solder on the interconnect, there's lots of value add that's provided here: solder joint reliability, improved signal integrity because of improved crosstalk, simpler design resulting in reduced irregularities, increased coplanarity, especially when you got larger arrays or multiple arrays across a carrier card, more consistent spacing between joints, improved yields, low temperature solder compatibility, tin whisker mitigation, and the like. We've created a white paper that talks about the solder column termination. It's available on our tech library on our website if you'd like to learn more detail about this technology, not only on Accelerate HD connectors, but also by extension on the QMC connectors that have been adopted by VITA 93. One more shameless plug from Samtec. Accelerate HD is really the first connector family using the same contact type and various other interconnect solutions that we have for applications outside of QMC. So, cable, single pair, dozens of pairs, hundreds of pairs. We've got combination connectors, Accelerate MP, power blades with the same interconnect. Accelerate HP is a little bit larger connector. It gets higher speeds up to 112 and the like. So key takeaways from Samtec's portion of the QMC ecosystem. Robert did a nice job talking about it. Hopefully we've added a different angle. VITA 93 QMC, next generation mezzanine, enabling modular, scalable design and rugged and reliable computing. You've seen throughout the ecosystem how or throughout this presentation, throughout Robert's presentation, how QMC by itself, whether it's a single door or quad module, is compatible with any number of carrier card form factors. So 3U, we showed earlier about 3U, 6U, Euro cards, VPX, compact PCI, compact PCI Express, compact PCI serial, et cetera, et cetera. VNX, obviously, which we talked about, VNX Plus, PCI Express, it's expansion cards, micro TCA, ATCA as well. So while QMC is a VITA spec, this will find broad adoption across the industry in a number of form factors. The VITA 93 QMC connectors are based on Samtec's Accelerate HD ultra-dense slim body arrays, basically faster, denser, smaller than previous generations of interconnect found on standard mezzanines within the VITA ecosystem. For more information on these connectors, samtec.com/QMC, or you can email us directly at qmc@samtec.com. Next, we're going to turn the rest of the presentation over to Jake from New Wave, and we'll look at, he'll give an overview of some new use cases around QMC.
Hi, everybody. I appreciate that intro, Matt. And, I really have the luxury here of going after Robert and Matt. They did a great job kind of introducing the standard itself and then the connector and what the connector is capable of. I'm going to take this and kind of run with a specific set of applications that we're really excited about and the sort of the why we're excited about that and what we think it can be. And specifically, that's getting into using QMC, the standard we're talking about here, the connectors, the stack up we're talking about here, as a SOM, as a system on module, as a compute module of all various types. And we'll get into why and how of that throughout this presentation. But really using it beyond I/O and even beyond the various VPX, VNX, kind of 3U, 6U backplane applications. And to kind of dive into that, the first I would say is you look at sort of the affordable mass demands in the aerospace, defense, military arena, drones, air launched effects, missiles, ground vehicles, backpack SIGINT and EW. There's a very clear demand, and Robert and Matt both touch on this too, to go smaller, go faster, go more economical. And I think QMC really has the opportunity to meet that opportunity in the market, both in backplane and VITA and VNX type applications, but also without those, backplanes and enclosures in a true SOM standalone type fashion. So we're going to get into that more. Quick look at this. Again, this was introduced already. I'm not going to go over things that have already been touched on, but on the far right-hand side here, you can see the single wide, dual wide, and triple wide QMCs. And we've talked about what it is. It is a SOM or mezzanine standard using next-gen connectors and speeds and interconnects with true ruggedization built in, right? These are developed from the ground up with a VITA 47 VPX kind of class ruggedization, connectors that are doing 32 gigabits per second or 64 on PAM4 type encoding. You have scalability. You're going, single wide, double wide, triple wide, and even greater. So you have this kind of scalable open systems architecture. And then you have pin density such that you can put very capable processors in a very small rugged package in an open systems type way. So we look at QMC and say, this is going to be for a lot more than I/O, kind of like finally a standard that you can actually use in an open systems way for compute type applications in mission critical ways. So moving into that a bit, if you imagine this as an 8.5 by 11 sheet of paper, a standard size sheet of paper, regardless of what screen and magnification you have while you're looking at this, imagine this as an 8.5 by 11 sheet of paper. This is to scale a single wide, double wide, and triple wide QMC. If you look at the dual wide in the center there, that is roughly the size of a standard business card. So if you can, a standard business card size, and then it has both a set of connectors at the top and the bottom, and that's in a dual wide that fits a VNX module also. As Matt and Robert talked about, that was designed to either put two singles into a VNX or a double into a VNX sized module. The scalability here allows you to put a single twice into like a VNX form factor, or a single double, or imagine a triple size slot where you could put a double and a single. So you've got this kind of mix and match open capability to start bringing in different combination, different processor types, IO types, storage, encryption, etc. So that gives you a good sense, at least in one slide here, of what size we're really talking about. I don't want to dwell on this too far because it's definitely been touched on, but it's not that we don't think IO cases will be solved with QMCs. Actually, I think QMC is going to be extremely successful in IO-centric applications. So if you look at QMC today, and then you look at what XMC and FMC have historically been used for, and you look at things like parallel IO, high-speed serial IO, avionics buses, optical, RF, networking. I absolutely am not here to communicate that QMC won't do those things. I think it will do those things. I think you will see a slow, because our industry, moves at a certain speed, but I think you'll see a very steady turnover of where XMC or FMC were historically used. I think you will see QMC. And I didn't mean to say slow in the sense that I think QMC is going to start being adopted right away, but I certainly understand and have been in our industry long enough to know that XMC and FMC will be around for a long time yet, where you already have designed in solutions or capability available, qualified, shipping and production. It's not that I think XMC and FMC are, going to be gone overnight or anything. They'll be around a long time, but I think you will see a steady and fairly consistent adoption of QMC for IO use cases in VITA 46, VITA 65, VITA 100, VITA 90, VNX Plus. I think that's a very solid expectation to have, that QMC will continually be leveraged into those standards and new modules. In fact, working like VITA 100 and VNX are mapping QMC directly to backplane IO channels, and mapped right into the base standard. So certainly QMC is seeing the adoption there. I wanted to hit on that because for the rest of the presentation, we're going to primarily focus on the non-IO use cases for QMC and the why behind them. So to go into that why for a little bit, I want to stress there's kind of two things that merge together here, and then QMC looks strongly like an answer to both. One is a very quickly growing demand for affordable mass systems in drones, missiles, backpack, EW, SIGINT, where we as an industry have the need to deliver smaller, more economical solutions that are to market fast, right? That's the other thing. They have to get to market much faster. It's not that today drones and missiles and other things can't be developed smaller than 3U and smaller than VPX. It's just when they're custom every time, the schedule that it takes to do that, you always have to incur sort of the full development cycle. We need, as an industry, to get these solutions to market much faster. So a standard like QMC that's inherently rugged, has high bandwidth capability, flexible, scalable sizes, allows the industry to invest in a standard and a standard set of offerings while meeting the demand to get these capabilities to market much, much faster. We see that happening in chassis solutions like VPX and VNX, but I think a big part of QMC's success is going to be even outside of those, where you're using, let's say, a drone body as the enclosure, and you need a truly rugged, truly deployable SOM, today to bring into that type of enclosure, where the drone is the enclosure itself. So the speed there is part of that open systems, and we talked about MOSA a little bit already in this presentation. VITA 93 certainly hits a MOSA concept in the industry. All right, so kind of why QMC, right? It is not lost on anybody that there are a variety of small form factor standards out there. And as part of our assessment of the need to get to market fast in a standards-based way, and then have the capability, right? The high density connector, the ability to put processors and GPUs and CPUs and FPGAs on these, we did a standards evaluation and said, there's all kinds of things out there, right? SMARC and COM-HPC and COM-Express and ModBlock 7, Q7, PC 104 stacks, it's been a long time. There is a lot of ways to go about this. but they all seem to fall short in one way or another, which is either they're not getting the next generation technologies of processors and networking equipment because maybe their connector stack doesn't handle that kind of speeds and rates, or maybe the connector stack does, but the ruggedization isn't there. So you can use it in the lab, or you could use it in kind of a development, but you'll never actually go to production with them. Those fail the test of, can I use this at speed? Can I get this out of the ecosystem, a commercial ecosystem at speed? And can I actually take it to production? And when you look at those two characteristics, QMC is fitting the bill, and fitting the bill really, really well. And that's exciting for, I think, the whole ecosystem, and that we really have a smaller than 3U rugged form factor that is open and can go to production. So that's really the combination things we see in QMC. All right, a little bit more on, you know, the size and the why. This is, again, to scale, obviously shrunken down to fit onto this presentation, but you see a similar view actually to what Matt presented, but kind of turned maybe a little bit, in the sense that on your screen you have a 2-inch, 4-inch, 6-inch diameter to scale, and then you have a VPX module, a 3U VPX module, an XMC module on the right hand side. And on the left hand side you have a dual width, again about the size of a standard business card, and a single width, which is going to be more the size of like a USB stick, a traditional USB stick, or a stick of gum. Both the dual and single wide QMC will fit kind of flat down or face down in both a 6-inch and a 4-inch diameter tube. Neither the VPX nor the XMC are going to fit in that diameter. They just are not going to fit. And even in the 2-inch, you could imagine a single wide turned the vertical way, you know, kind of along the enclosure wall or through the middle of the enclosure wall. Even that would fit into a 2-inch. So when you look at where can this go compared to where some of the other standards are possible to go, you can see where QMC can be really exciting. Again, there are maybe other things that can go in there, you know, custom SOMs, proprietary SOMs, but now you're not in an ecosystem. You have no real expectation that a next generation processor or an alternative compute solution or storage solution or networking solution would exist in that form factor. So again, you're kind of back to scratch, where QMC genuinely solves that problem. Matt touched on this a lot, so I probably am not going to spend a ton of time on this, but if you look at the connector density, so that's the right-hand chart on this slide, compared to even FMC Plus or HSPCE, you're looking at you know, a 2x connector density advantage with QMC. So you're getting true just density doubling here, essentially. And then from an area perspective, unlike an FMC or an XMC, where you're essentially locked from the standard to one size, on the left-hand chart here, you can see the scalable nature of this, where you can truly scale up or down using the same overall standards basis connector set format, from a single, double, a triple, a quad, and there's even a 5-wide not showing here. So you have true scalability while still doubling the density with your connector. In the end, when you double the density of your connector and basically double or more the signal integrity, the throughput of that connector, again, I'm touching on Matt's material a little bit here, you're looking at like a 5x improvement from XMC to QMC in even a smaller size of overall throughput. So when you talk Gen 5 PCI Express or 100 gigabit Ethernet into a size smaller than XMC, you know, again, back to like that business card type size, you can actually use those type of networks, 100 gig Ethernet, let's say, in that size, which is going to be extremely important in VNX, but it's going to be extremely important even outside of VNX in those small 4-inch, 6-inch diameter type applications, to move data around from sensor to compute, or from compute to storage, or compute to communications, etc. I want to give a couple examples of where this is actually being used in practice, so people can get an idea of how it's going to be deployed. The first one you're seeing here is a 3U VPX module. It is you know, VITA Standards SOSA aligned module. You're seeing it with a transparent cover here. You have to look a little carefully, but in the front there you can see where you may have typically seen maybe an FMC site. there is a dual QMC site available. This, again, is using the fact that we have more connector contacts and we have higher signaling rates through them. So by having an open QMC site, a dual wide open QMC site, and this is an FPGA module, we can now bring higher density optics, higher performant RF, A to D, other accelerators, think an AI accelerator, or maybe more storage or memory, crypto engines, etc., can all come in to that dual wide open QMC site. So that is a use case that we see it's going to be heavily used, and I would expect to see on a wide variety of modules coming to the market. Not just in 3U, but 6U, 4U, VITA 100. I think they will all use that style of mezzanine option, expansion option. But that same exact form factor, that same exact infrastructure can also be taken, again, and what we're primarily focused on here is that compute-centric SOM. And this SOM is usable and attractive in a 3, 6U, VITA 100 or VNX situation, but I think is also extremely attractive in just taking that COTS standards-based SOM with this great set of connectors and mechanical infrastructure essentially, and bringing that into housing that might be 4-inch, 6-inch drones, air-launched effects, ground vehicles, backpacks, etc. There's a huge attractiveness to having a standard that actually meets that moment. So 2 use cases, it's the same exact footprint, whether you're putting that into 3U or whether you're taking the SOM and putting it into some other enclosure. And that's really part of the attractiveness, right? You want reuse, you want scalability, you want composable architectures where you might use this exact same SOM or similar SOMs in a application in a backpack where it is not in a chassis-based design at all, and then over into a chassis where it's the same algorithms, the same software, the same application, the same skills being deployed. So I know I'm getting close to time here. I want to hit the last slide. Where does this all go? In summary, we absolutely think it will be adopted. QMC will be adopted as a standalone SOM that really meets the ruggedization plus performance plus economy of scale essentially in the market, while also being used in all kinds of rack-based, backplane-based standards, 3U, 4U, 6U, VITA 100, VNX, compact PCI, etc. It has the environmentals to actually go to production as a SOM. It has the standards such that you can expect and anticipate a wide offering range from the whole ecosystem. And that's kind of the last thing I was going to touch on is I would expect that there's going to be a wide range of offerings, IO, RF, processing, including CPUs, GPUs, FPGAs, SoCs, AI accelerators, and not just one, right? You look at sort of the range of performance you could have when you go from single wide to double wide to triple wide, and the different ranges of processors. I can imagine very diverse applications accepting QMCs in a wide range of power and performance packages, essentially. Storage, crypto, security, and networking are all additional ways QMCs are going to be utilized, and we're excited for it and looking forward to working with all sorts of different people in this ecosystem. So with that, I got to turn this over to John here, and I think we're going to Q&A.
You are correct, Jake, and thank you and Matt and Robert for some presentations. Let's get right to it. I got a question here for Robert. Can system designers mix QMC modules and carrier cards from different vendors together?
Yes, that was the initial thing. Our mantra was kind of any QMC on any carrier card. So they were designed to have multiple, like on a 3U VPX, you could put probably 3 cards mixed from different vendors. Even a fourth 3 different QMC vendors and a 4th carrier vendor. So it all interacts and operates seamlessly.
Okay. I've got a question here for Jake. What makes QMC SOMs more attractive than non-standard SOMs? Maybe even SOMs using Accelerate HD connectors.
Yeah, that's a great question. I mean, certainly there are SOMs in the market, right? Systems on modules in the market, and there's SOMs that even are probably using those connectors. The thing I would say is without a standard, without an open system, you can't reasonably expect that you're going to be able to get a tech refresh, a different processor, an adjacent type of technology, maybe a GPU to a SoC or something like that. So I do think being standards based and the speed that our services want to bring capability to the field, I think it's critical to be in a standard. So QMC really fits the bill there.
All right, Matt, can you comment on what industry standard carrier form factors will accept QMC mezzanines?
Sorry, you cut out there for a second, John. Can you ask that one more time? I'm sorry, sir.
Talk to what industry standard carrier form factors will accept QMC mezzanines.
Oh yeah, sure. We talked about that a lot through all three parts of the presentation. Robert talked about it. Jake did. I did. But just to drive that point home, obviously VNX Plus, compact PCI, its various flavors, serial, express, etc. VPX, in its various flavors, micro TCA, PCI SIG, ChemAIC. So, the fact that you have so many ecosystems available really show the flexibility of QMC. And it's also why, Robert, Jake, myself, several other ecosystem contributors are real excited about the future in terms of flexibility and scalability of the platform.
Okay. Matt, I'm going to go right back to you. I got a question here from the audience. Are there any other stacking heights for the Accelerate IO connector family planned for the future?
Currently, we support 5 to 16 millimeters in full millimeter steps, so 5, 6, 7, 8, all the way up to 16. There's potential to expand it beyond that if there's a need for it. If you have something that's outside those ecosystems, we can't go shorter than 5, but we may be able to go taller than 16. Just contact us directly with your application, and we'll take a look at it.
Okay, Jake, I got one for you. There was a processor version of PMC called PRPMC or VITA 32 or maybe 36, the questioner's asking, that really didn't take off in this person's opinion. Why would you think a PRQMC would be a business success? Why not just plug IO QMCs into a processor-capable carrier card instead?
I think the real emphasis there would be on size, right? It really is a size thing. I mean, sure, PMC has actually, there's XMC processors too, right? There's a lot of XMCs out there today that carry FPGAs or x86 or what, they just don't fit. There is a physical size sort of problem with PMC, XMC from that perspective. I look at QMC, especially the dual wide. I think that's a sweet spot in the fact that you can get meaningful processors in a smaller package in a standards-based way, right? There are some out there, but they're not standard. You have no reasonable expectation to believe that you're going to be able to bring in tech refresh or different capability.
Okay. I got a question here for Robert. This person is asking, can you talk a little bit about how QMC QTM supports galvanically isolated IO interfaces?
Yeah, sure. That was one of the things that, we were working in the work group. We knew that isolated IO modules, whether it's analog or digital or serial communication, we saw those in a variety of different platforms, even dating back to the old industry packs used on VME. So when we were designing that, we really, made sure with the pin maps that we had the grounding and that the carrier cards could support to isolate the signals as well. So the QMCs will happily support isolated interfaces for the systems.
I remember Industry Pack. That's really throwing an old standard out there. So let's got another question. This one is not assigned, so whoever wants to grab this one. Are there any host CPU boards in VPX or VNX that have QMC sites available today?
If they're not, there will be.
Yeah, I'll jump in there too. I know of a few, but I'm not going to name vendors and so forth on the call. But yeah, I know of a few.
Yeah, I've seen some people sharing them around at trade shows that there is one. I believe it was with like a Tiger Lake processor and 2 QMCs sites on it, but it hasn't been released to market yet, though.
Okay. Next question. Once again, not assigned. Are there dedicated pins for analog digital video signals?
No. Well, that's up to the QMC designer. We assign the I/O pins. I mean, you've got 40 I/O differential signals. So, or I'm sorry, 20 differential signals, 40 I/O. The QMC designer can decide what goes on those pins for the I/O. So, you need to arrange them as I/O pipes. So you need to kind of group them accordingly and mind the grounds. But there is no, this pin has to be analog, this pin has to be digital, this has to be video. That's up to the QMC designer.
Okay, I got a question for Jake. What is meant by standalone QMC?
So what I mean by that when I say that is certainly it's a VITA standard, and there is going to be a lot of utilization of QMC in VITA 46, VITA 65, VITA 100, and VITA 90. So you look at those standards, and they're all going to incorporate VITA 90, and the various people building modules in those standards are going to incorporate a VITA 93, right? So they're all going to pull in QMCs. When I say standalone, I look at that as a very legitimate use case where you take a VITA 93 module, probably like a processor or SOM module, and use it in let's say a 4-inch diameter tube without any other VITA stuff around it, essentially. No 3U VPX module in there, no VNX module in there, just you need to get in a 4-inch diameter tube. You've got the shell of your, let's say, drone is 4-inch diameter, and you need to get electronics in there, and it's got to be rugged, it's got to be capable, and it's got to be now. I think you take one of these VITA 93 SOMs, system on module, and you basically button it in or strap it in to that enclosure, and there is no other VITA infrastructure around it. That's what I mean when I say standalone VITA 93.
Okay. Question for Matt. Will QMC replace other VITA mezzanines like PMC, FMC, and or XMC? Is there a timeline for that, if so?
Good question. I don't know if it'll replace it, but I think and I think Jake did a nice job of mentioning this, is, FMCs, XMCs, PMCs, they've been around for a long time, and I think they'll continue to be used in use cases going forward. But for a number of applications where, smaller, faster, denser, is needed, especially from a mezzanine standpoint, QMC is going to ramp up where there's, probably a slower, longer ramp down with FMC, XMC, PMC. Time frame on that, FMC, Samtec still, we see a ton of activity around XMC and FMC, FMC plus, XMC plus. Don't see that going away anytime soon, John, but I anticipate that we'll see accelerated adoption of QMC given the value add over the next year to two, especially as the ecosystem continues to expand with the various I/O modules, the compute modules that Jake talked about, and the like.
Okay. Question for Robert. What is the height limit for placing components under a QMC module?
Well, it kind of depends, because as you saw that Matt was showing you that there's a variety of different stack heights with the connectors. So the QMC module has a 7.5. So if you would mate that with, say, a 6.5 on the carrier card, the QMC for the heat sink, it uses 4.7 millimeters. So if you've got a 14 millimeter stack, you've got another 10 millimeters under, almost, or sorry, what was it, 9.3 underneath there. So you could put like a processor chip underneath there and cover it with a heat sink. You could put a Ethernet controller under there. We've shown on our carrier, you could even put a fan underneath there. So depending on what kind of platform you're using, you might be able to put quite a bit. Even on like the VNX module, which we're using, was it a 9 millimeter stack? You still have several millimeters underneath there to put components, and then put a heat sink on top of that and use conduction cooling to wick away the heat.
Okay. I got another question here, not assigned. So if anybody wants to grab it, just give a shout. Are there plans for any QMC stack heights shorter than 9 millimeters? Who wants that?
I don't think that, because, well, the QMC has a 7.5 millimeter, which means on the carrier you'd be using the 1.5 millimeter. I don't know, Matt, whether you're planning on, I don't think you said you're planning on anything shorter than that.
Well, the shortest stack height on the connectors is 5 millimeter. So theoretically, you could get something that small. Whether that's adopted by the standard or not, is another discussion.
Mm-hmm.
Okay. So yes, theoretically, it would be possible to make a QMC module with a 5 millimeter stack height, but whether that would be VITA 93 or compliant or not, that would need to be considered.
Okay, just got time for a couple more questions here. Jake, what are the power and thermal limitations using QMC?
Yeah, certainly. When you go smaller and smaller, but yet you want to put these next gen, processors or GPUs or on there, there are limitations, right? I mean, there is just it's just physics of, how much power can you put into this space versus how much can you cool in that space. And then you have considerations for conduction cooled or liquid flow through, not through the card, but like through a chassis. I think in like a dual wide QMC, you're probably looking at 60-ish watts as an absolute, kind of max, just physical limitation there, especially at 85C. So there are some limits, of course.
Okay. This question is unassigned, but fairly detailed. The clearance hole specified on the mechanical layout diagram, 1.7 millimeters plus 0.1/0 are very tight with respect to the 1.6 millimeter fasteners called out in the standard. Have there been interference issues in a conduction cooled application? I'm going to throw it at you, Jake, since you just were talking about thermal management.
Yeah, so I would say yes. I mean, there are trade-offs in everything in engineering, right? I mean, there is at times a desire maybe to flip the hot components to the other side, right? There's a primary side and a secondary side. Certainly there are use cases where flipping, the hot side to the other side would be desirable, but there's use cases where it's undesirable. So trades have to be made. You have to make sort of, your keep out regions, your profile, so that you have an ecosystem here. And absolutely, there are times where you wish you could flip it. Now, good thermal slugs or heat pipes take care of that problem, right? Or largely take care of that problem by pulling the heat kind of to the case.
Okay. Another one along those lines: proven ruggedness of connectors and long pin PCB against shock and vibe. I mean, I think it's a question. Is there proven ruggedness of connectors and long thin PCB against shock and vibe? I'm guessing that's the question.
Well, yeah, the short answer is yes. Obviously, any QMC on any QMC carrier is going to have to be submitted to the test requirements of the environmental requirements of their ecosystem, John. But this family of interconnects has been around for a long time. It's in a number of applications. They're used in space, they're used in automotive, they're used in transportation. So there's a lot of data that we can share, under NDA or directly with an OEM to kind of answer that more application specific. Again, the listeners can contact us offline to address that specifically for their use case.
Okay, just a couple more questions here. Matt, once again, talking about your connectors, it was mentioned that the QMC connectors are based on Samtec's Accelerate HD connectors. Are there other standards using similar solutions?
The short answer is yes. So, those are several PICMIG standards, some SCET standards. There's some other VITA standards as well that use these. So again, widely adopted within open standards. There's also some de facto standards using Accelerate HD for SOMs that Jay kind of alluded to. So it's a widely popular family. It's used in a number of solutions, and the market has done a really nice job of adopting it in other spaces that we never anticipated.
Okay, I got a question here assigned to Robert. Are carrier backplane profiles or pin maps defined for QMC modules?
Yeah, we've been working with VITA 90, so we have defined slot profiles and pin maps for a double QMC carrier card. On that, we've also been working with the VITA 100 to make sure that there's profiles in there as well to accommodate QMCs. Unfortunately, with VPX, like OpenVPX, VITA 65, it was done before then. But what we're doing is we're really reusing the XMC pins, the XMC overlays, to be able to use those pin map definitions in that way. And we're going to continue to work towards that.
Okay, I think this will be a good question to end on, and it's for Jake, and it might have been touched on earlier, But Jake, how long will QMC adoption take? How long's the process?
Yeah, I might have stumbled through that when I was presenting. Here's the thing. I think it's very soon where you're going to start to see the uptake, right? And you're going to see it on single board computers. And there was a question asked about, when do I see an SBC with a QMC site? There's some out there already being floated around. We're doing an FPGA card with a dual QMC site, so I can show you that one if anybody's interested. So I think it's immediate, or this year, 2026. But that doesn't mean FMC and XMC just go away, right? They're going to be here for another decade too. So you're going to have this parallel, kind of situation, and that's okay. So I think it's immediate, but steady. You're going to have the other ones around a long time.
Okay, and that brings us right to our time limit for today. Sorry I couldn't get to all of your questions. So I'm going to get back to you after the event with more information. I want to thank Matt, Jake, and Robert for speaking today, and Samtec, New Wave, and Acromag for sponsoring this webcast. This and all Open Systems Media webcasts are copyrighted. It may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as the URL shown on your screen, and be available for at least 1 year. I look forward to seeing you on future Open Systems Media webcasts. Goodbye and have a great weekend. Thanks, gentlemen. Excellent job.
Thank you.
Thank you very much. Thanks, guys.